Okay, so until now we have derived two equations of motion and an extra formula. First, v is equal to u plus at, then s is equal to ut plus half at square, and then another extra formula which is s is equal to u plus v by 2 into t, that. So now we will be deriving another equation. Again, for that we'll be using the first equation of motion as the base, which is final velocity v is equal to initial velocity u plus acceleration and time duration product. Okay, this is the base. So suppose we square both sides, okay, LHS and RHS, that is v square is equal to u plus at whole square. Okay, we have squared both sides. Now we will open it up. That is v square is equal to u square plus 2u at plus a square t square. Okay, this. So here we can write it as v square is equal to u square plus, here we are taking 2a common. Please notice 2a common. So ut plus, here there is the extra 2 in the numerator, so we have to put 1 in the denominator here. One a is here, so it will be a t square, this. Okay, confirm it, 2a ut, same. Then 2 gets cancelled in both the numerator and denominator, and we have a square t square. See, 2 gets cancelled, a into a square, then t square. Okay, it's correct. Okay, so now if you focus on this part, ut plus half at square, then you remember the second equation of motion is s is equal to ut plus half at square, where s is the displacement. Okay, displacement, s is equal to ut plus half at square. Okay, so we will substitute this ut plus half at square with s. Then this whole equation, it becomes v square is equal to u square plus 2as, or we can write it as v square minus u square is equal to 2as. So any way you write it, it's correct. Okay, so this is another equation of motion, basically the third standard equation of motion. Okay, v square minus u square is equal to 2as. So here is there is another way also in which we can derive the same equation, okay, the same expression. Now we know that acceleration is rate of change of velocity. Okay, so here acceleration, we can write it as dv by dt. Okay, derivative of velocity with respect to time. Now we can manipulate this dv by dt and express it as, okay, please pay attention here, dv by dt, I am writing it here as dv by ds, okay, dv by ds into ds by dt. Okay, dv by ds into ds by dt, same, ds gets cancelled from both the numerator and denominator, we get dv by dt. So same thing, we are just manipulating it here. So it becomes dv by ds into ds by dt is nothing but v, velocity v. So it is dv by ds into v. Okay, velocity is displacement by time, derivative of displacement with respect to time. Okay, ds by dt is equal to v, we know that. So this is the expression, a is equal to dv by ds into v. Now this becomes v dv is equal to a ds, this. So if we integrate both sides, the lower and upper limits, here velocity is the variable parameter. Now we know that the object, the whole movement of object, the time, the initial velocity, final velocity, displacement all stays the same. Okay, first observation started at t equals to 0 with initial velocity u, observation ended at t equals to t seconds with final velocity v, constant acceleration a, displacement s. This thing stays the same in every equation. So here the lower limit is the initial velocity u, the upper limit is the final velocity v. For the displacement s, which is the variable parameter here ds, the lower limit is 0 because at time t equals to 0 the displacement was 0, and the upper limit is s, the final displacement s. So here a is constant, so it comes outside the integration and it becomes v square by 2, okay, v square by 2 with v and u the upper and lower limits. Here it is a into s, this is s and 0, the upper and lower limits. So this becomes definite integration, putting the upper and lower limit values here, v square minus u square by 2 is equal to a into s minus 0. That implies v square minus u square is equal to 2as. Okay, v square minus u square is equal to 2as, which is nothing but the third equation of motion which we had derived previously. V square minus u square is equal to 2as. So this is another way of deriving the third standard equation of motion. Okay, so you can do it this way, it is correct, you can do it this way too. Okay, this is the first method, this is the second method. Okay, so far we have discussed, we have derived 3 equations of motion. So here we'll be discussing and deriving another equation of motion which is related to the displacement. Okay, the displacement of an object in a particular time duration. Okay, so let me explain what I'm trying to say. So let us say an object, okay, it has started at some time instant, let's say t equals to 0. It has an initial velocity u and is traveling along a straight line with constant acceleration a, like this. Okay, here this is the final point where observation ends. This is t seconds, the total time duration, and let's say we want to determine, we mark points, okay, of 1 second duration each. Okay, here one, here one, here one, like this, each of 1 second duration, and we want to determine how much displacement it happened in each of these durations, in particular durations. okay, this, like this. Suppose this is 1 second, this is 2 seconds, this is at 1 second, this is at 2 seconds, this is at 3 seconds, this is at 4 seconds, let's say like this. Suppose we want to determine how much displacement, the object was, how much it got displaced in the duration from 1 second to 2 seconds. In this time duration, okay, how much displacement happened. Similarly, from 2 seconds to 3 seconds, how much displacement happened, okay, this. Then from 3 second to 4 second interval, how much displacement happened. This we are trying to determine. This is called as displacement of the particle during the nth second, this particular nth second. So here, let us say we consider the same thing, okay, the object starting with initial velocity u at time is equal to 0 seconds, okay, this here which final velocity v, okay, and let us say we want to determine the displacement of the particle at some particular duration t equals to n seconds, okay, and we just determine another time instant 1 second away from it, let's say t equals to n minus 1 second. We want to determine this displacement in between these two time instants, which is called as the displacement during the nth second, this. So for that, what we can do, first we have to determine the displacement of the particle for the entire n duration, that is from here to here, this one, and then during the n minus 1 second from here to here. So when we subtract Sn minus Sn minus 1, we get the displacement of the particle during the nth second, which gives us the displacement from n minus 1 to n second. In that particular instant, n minus 1 to n seconds, which I was talking about, okay, 1 to 2, 2 to 3, 3 to 4. If you notice, here the time duration is 4 minus 3 equals to 1 second gap. Here also 3 minus 2 equals to 1 second gap. Here 2 minus 1 equals to 1 second gap. They are 1 second gaps, okay, 1 second time gaps. So this is called as the displacement during the nth second. That is the displacement happening between any time instant n and n minus 1. That gap between n minus 1 and n seconds. This. So that will do. So here we'll be using the second standard equation of motion, which is S is equal to ut plus half at square. This we'll be using. So first we have to determine Sn. Sn, simply we substitute t with n, displacement during n seconds. So it is un plus half an square. This is displacement during n seconds, this one. Then we have S n minus 1. Simply we substitute t with n minus 1. So here it becomes u into n minus 1 plus half into a to n minus 1 whole square. Okay, so this becomes un minus 1, or simply un minus u plus half a into n square minus 2n plus 1, this. Okay, this is this Sn minus 1. So, in order to determine the displacement during the nth second, it is simply Sn minus Sn minus 1, this. Okay, this one. So, here it becomes un plus half an square minus un minus u plus half an, okay, half an square, I am simply opening the bracket here, half an square minus an, okay, minus an, 2 gets cancelled, it becomes minus an plus a by 2 plus a by 2, this one, okay, plus a by 2. So, here it becomes un plus half an square minus un plus u minus half an square plus an minus a by 2, this. So, this is equal to u minus un gets cancelled, plus half an square minus half an square gets cancelled. So, this becomes, that is equal to u plus an minus a by 2, this. Okay, u plus an minus a by 2. So, this is equal to, if we take a as common here, u plus a to n minus 1 by 2, that is equal to u plus a to 2n minus 1 by 2. So, this is the standard equation, which is the displacement during the nth second is equal to u plus 2n minus 1 by 2 into a. So, this Snth means displacement during n seconds minus displacement during n minus 1 second. Okay, so 1 second gap, 1 second time gap. This, always remember this. What is the significance of this equation? This is the fourth standard equation of motion. Okay, this u, initial velocity u plus 2n minus 1 by 2, where n is the particular time instant for which we have to determine the displacement, and then the constant acceleration a, okay, which we have demonstrated here. This is Sn during n seconds, this is Sn minus 1, displacement during n minus 1 seconds. This difference, which happens over this gap of 1 second, because n minus 1, it is equal to 1 second. This displacement during this 1 second duration is the Snth, this one, this 1 second duration from n minus 1 to n. This we have determined, this one, this one. Here. Okay, so here we have discussed the 4 standard equations of motion. Okay,